G'day everybody, happy Monday the 7th of January. Sorry I didn't do any streams over the weekend. We are back with another Exercism Elixir problem. If we jump over into Exercism, you can see that it's a site that helps you practice your programming in a number of different languages. I've joined a number of different tracks. I've got Elixir, Elm, JavaScript, Python, and Ruby. The ones that I stream daily are the Elixir track. So the Elixir track is over here. And today we're doing the Hamming problem. So I haven't looked at this problem yet. I like to solve all of these fresh. I'll read the README after I download it, and that way you can actually see my approach to solving some of these problems. Let me pause my music and we'll jump straight into the Hamming problem. So I've just copied the download link there. I'm going to jump into iTerm and download it. Okay, so that's just downloading now. We'll jump over into VS Code. I apologize if my keystrokes aren't that accurate today. I've messed up the spacebar on my laptop and I'm using a Bluetooth keyboard and I'm not quite accustomed to it. Let's jump into Exercism Elixir and we'll read the README for the Hamming problem. So yes, as always, jump straight into the README and we'll read it. Hamming. Calculate the Hamming difference between two DNA strands. DNA again, just like the RNA transcription one. A mutation is simply a mistake that occurs during the creation or copying of a nucleic acid, in particular DNA. Because nucleic acids are vital to cellular functions, mutations tend to cause a ripple effect throughout the cell. Although mutations are technically mistakes, a very rare mutation may equip the cell with a beneficial attribute. In fact, the macro effects of evolution are attributable to the accumulated result of beneficial microscopic mutations over generations. The simplest and most common type of nucleic acid mutation is a point mutation, which represents one base with another at a single nucleotide. By counting the number of differences between two homologous DNA strands taken from different genomes with a common ancestor, we get a measure of the minimum number of point mutations that could have occurred on the evolutionary path between the two strands. This is called the Hamming difference. It is found by comparing two DNA strands and counting how many of the nucleotides are different from their equivalent in the other string. The Hamming distance between these two DNA strands is 7. So let's take a look at these two DNA strands and see why. Okay, so the first one there is G, it's been replaced by C. A is the same there, T is different, G is different, T, A is the same, A is different. So it's literally just the number of differences between these two strings. The Hamming distance between these two DNA strands is 7. Implementation notes. The Hamming distance is only defined for sequences of equal length. So an attempt to calculate it between sequences of different lengths should not work. Okay, so we've got one point about our implementation here. We should have some sort of validation there that prevents strings of different lengths from being compared. The general handling of this situation, e.g. raising an exception versus returning a special value, may differ between languages. So generally in Elixir, we return an error as a tuple rather than raising any errors. So typically in Elixir, you wouldn't raise any errors. Running the tests, okay. So this is always something I do just to make sure that the test function is named correctly. We'll jump over, run the test. And okay, we have a failing test, we have no implementation. Let's jump over into our hamming.exs and take a look at the documentation and the spec here. So it returns the number of differences between two strands of DNA known as the Hamming difference. Hamming distance, sorry. Examples, Hamming distance between those two, okay, 4. Okay, so I see here that it's returned a tuple of okay and the distance. So that to me implies the fact that if the distance is wrong, we're going to return an error and potentially have another atom in there explaining what the error is. So let's jump over to the Hamming test and just get an idea of what we've got here. So no difference between empty strands. So if we pass in empty strands, we get okay and a Hamming distance of 0. Hamming distance between strands of, no difference between identical strands, okay, Hamming distance of 0. Small Hamming distance in middle somewhere, okay, so that A and T are different, so we have a Hamming distance of 1. Distance with same, nucleotides in different locations, okay, so T and G in this one are replaced with G and T. A is the same, so we have a Hamming distance of 2. Larger distance, okay. Hamming distance is undefined for strands of different lengths. Okay, so here we've got the error that we need to return if the lengths are different. So we can probably start with that sort of validation, but I think that we'll just jump straight into actually doing the meat of the function, and then we'll deal with those validation tests a little bit later. So if we jump back into our implementation, let's have a look at our spec to see, okay, so the spec is actually wrong. So it says here that what we should return out of this, well, actually first let's look at the input arguments. So our input argument is a list of characters, 2 lists of characters as strand 1 and strand 2. And in the spec, it's got the return as a non-negative integer. Now, I know by looking at the tests that that's wrong. So what we actually want is OK and a non-negative integer, or error, as you see here, error and a string. So what we'll do is we'll fix that spec, okay, because we'll either return OK and then non-neg integer, okay, or this is the other option. We have error and then we have a string. Okay, so we've just fixed the spec. Now let's think about how we're actually going to implement this function. So, excuse me, if we go back to, or if we think back to our RNA transcription one, we were dealing with char lists as well. And I think that because we're dealing with enumerable lists and we're returning something that is some sort of summary of that enumerable list, it's very likely that we're going to use enum.reduce in this problem, but I'm not 100% sure. So let's take one of the test examples and use that as a way for us to determine. I like this one because it's nice and simple. We have 3, we have TAG and GAT. So we have TAG compared with GAT. So it looks like what we're doing is we're taking each one and comparing the equivalent one in the other string. So for instance, we'll start off and let's say we could somehow extract the T. Let's see, extract the T and the G in a tuple, right? And then if they're different, add 1 to our accumulator, right? So that would take the accumulator from 0 to 1, right? And then let's say in our next iteration, we could get A and A, and that would take our accumulator from 1, and we would leave it at 1 because they're the same. And then if we had the next one, which would be G and T, we would take our accumulator from 1 to 2 because they're different. So if we could get something like that, I think that would be very useful for us. I'm just thinking of the way that we could produce this. So really what we want to do is we'd like to take these 2 char lists and zip them together, right? So if we could have some sort of function that we could pass TAG, GAT, and what we get out is a list of this T, G, and then A, and G, put that in a tuple, G and T. Okay, so if we have some sort of function that can do this, I feel like there's a function called enum.zip that we could use, and I'm not 100% sure, but this could be it. Enum.zip, let's have a look here. Zips corresponding elements from a finite collection of enumerables into one list of tuples. The zipping finishes as soon as any enumerable in the given collection completes. Okay, so yeah, that's exactly what we want. So enum.zip is what we want, and let's start this by literally just taking our enum.zip, strand 1, sorry about my keystrokes, strand 2. And what we'll do is we'll jump straight into IEX and start having a look at what's coming out of our function. So I'm going to jump into IEX. What I've done here is in the test file at the top, they've got this code load file, and this is actually loading the module that we define in the Hamming file. So I just copy that and I paste it straight into IEX, and that pulls in our module that we've defined here, and we can start using it in IEX. So if I start doing Hamming, I've got the Hamming distance there, and what we can do is pass in our TAG, comma, GAT, and see what comes out based on our enum.zip. Cool. And as you see there, we've got numbers, right? So what that is due to is that here a single character is just going to be a char code, right? So for instance, if we do io.inspect and we have T, that's a list. That's actually a list. It's called a char list. And if we inspect that with char lists as list, that's going to show T as a list, right? That char list as a list. So we have a char point of 84. And that just means that the char code, if we were to do something like this, 84, that would print out T, right? Because 84 is the number for T, and Elixir is interpreting it as a char list unless we pass that option to inspect it as a list. So that doesn't matter. Basically, instead of comparing letters, we're just going to be comparing integers, which is totally fine. So now that we have enum.zip, what we'll do from there is we know that we would like to enumerate over each one and increment some accumulator if they are the same or if they're different. So to do that, we're going to use enum.reduce. So that's any time that we have some sort of enumerable that we want to turn into an enumerable of different length or some other accumulator. So what I'm going to pass in here is the accumulator initially. So we're going to assume that before we've done anything, our Hamming distance is going to be 0. So before we've iterated, the accumulator will be 0. And the next thing we pass in is our function. So the thing that our function is going to get is a tuple of, so we'll have like, let's call this char 1, char 2, and it also passes in the accumulator. So the first thing we can do is let's just inspect what's coming through. Let's inspect char 1. Let's inspect char 2. And let's just return a tuple. Let's just return the accumulator, right? So this is just going to spit out 0, but it's going to show us what each of our accumulations is. So here we're just going to reload the code again, and we'll run our Hamming distance on those. So you can see here we have the first 2, second 2, and that. So really what we can do here is, if you remember from the comment up here, we have this case, right, where T and G are different and we increment the accumulator. So what we can say here, let's just chuck in an if. If char 1, because again they're integers, is not equal to char 2, what we're going to do is we're going to add 1 to the accumulator, else we're just going to return the accumulator and not modify it at all, okay? So that's expressing exactly what we had here. So if I run this code again, we should get a Hamming distance of 2. And that's exactly right, because we have T and G going in. In the if statement, we have char 1 not equal to char 2, right? Because T is not equal to G. We increment the accumulator by 1. The next iteration, we have A and A going in. Char 1 and char 2 are equal, so we go to the else, and we just return the accumulator without adding anything on. So in the second iteration, the accumulator will be 1 as it gets passed in. In the third iteration, the accumulator will be 1 again. We have G and T that are different, and because they're not the same, we add 1 to the accumulator again. So I think that from this, we are probably able to start passing some of our tests, and what we can do is jump back out of here and run the test and see if we pass that first one. Okay, so I can see that what we've messed up here is that we're just returning the output of that enum.reduce, right? Which is just going to return the Hamming distance. So what we'll do is we'll say Hamming distance is equal to that enumerable, format the code, and then what we'll do is we'll just return OK and the Hamming distance. And we'll run the tests again, and we should pass on this one. Okay, and the reason that we've passed on that first test is because we've passed in empty strands. When we zip it up, we're going to have 2 empty lists. Anytime that we do an enum.reduce on an empty list, we're just going to return the initial accumulator that we pass in, so it's going to be 0. Let's uncomment the next one, or let's comment the next pending one. Okay, so the identical strands, what we have there is essentially each one being identical, so we just return the accumulator. Excuse me. So it'll be 0 again. Let's get rid of that. So a small error in the middle. Okay, and we've passed that one. Distance with same nucleotides in different locations. This one should pass as well. Very nice. And I think we're very close to passing all the tests. This has turned out to be quite an easy little one. We've approached it in the correct way. So these are going to fail because we don't have any error handling, right? So let's have a look. So the reason that one's failed is because we've passed in the tests, we've passed in nucleotide strings of different lengths. And from the documentation, you'll remember that they say that anytime we can only calculate the Hamming distance between nucleotide strings of the same length. So what we need to do is implement some sort of error checking in here or validation to make sure that they're both the same. So the way that I'm going to do that is with a guard clause. So I'm going to put in a when here, and what we want to say is when the length of strand 1 is equal to the length of strand 2, right? So we're going to assume that we always get in lists, and this guard clause is going to make sure that this clause of the function only gets called when the lists are the same length and we're able to calculate the Hamming distance. So now that we've got that guard clause, we need to have another clause of the function in here where in case there's an error or a specific error, we can return the error out. So this default clause is going to run when they're not the same length. And what we're going to do is we're going to return error. And let's have a look at the test file to make sure that we know what the error that should be returned is. Lists must be of the same length. So let's return that over here. And I think this test should now pass. Beautiful. So we've actually passed all the tests already. We're only 18 minutes in. That was a very quick one. Excuse me, I have something in my throat. I'm going to remove my comments. I'm going to check if there's any opportunity for refactoring or improving this at all. We did already change the spec of the function earlier on because the spec was wrong initially. I'm actually do a pull request on the repo for this one to update that. I think we're good. Now that I've removed those comments, this is exactly the same. I mean, we could, if we wanted to, turn this function into its own function, but I think honestly the length of the function is so small that it's not really worth it. So let's run that test again now that we've removed the comments. Anytime you make a code change, just make sure to rerun the tests. And I think we're good. So let's submit this and we'll do hamming.exs and we're all good. So I'm going to have a look at that solution. I'll share this in the article that I make to accompany it. I'll update the description of the video on Twitch and YouTube, and it will link to an article on my website, toptechskills.com, where you can see the explanation of the solution. So for the previous ones, for example, or your base problem, I have an article on here that basically just explains the way that I've approached the problem. There's a link to the video and just some more excerpts from the code and explaining my logic for doing it. So if we jump to Hamming, this is my solution here. I'll have a link to that as well. We're going to mark this solution as complete. And actually, just because I've been streaming for such a short amount of time today, I'm going to run through actually updating the repo to fix that mistake in the spec here, right? So I already have, if I jump over to source tree, I should already have the, let me just close out of these. I should have the Exercism repo in here, which has all of the documentation for all of the problems. So Exercism Elixir, where are we? This one. Let's open it up. I've already got my fork of it on GitHub. So if I show you that, let me jump over to GitHub, and that will be Percy Grunwald, which is my GitHub account. I'll just make sure that I have that fork in there. Let's have a look here. Repositories. Where are we? Sorry, I can't. Here it is, right at the top. How did I miss that? Apologies. So this is my fork, right? The original is over here. What I'm going to do in source tree is just do a fetch. I'm going to fetch the Exercism Elixir one from both the origin, which would be my one, and upstream, which is the actual Exercism one. Let's have a look. So it seems, I don't think they've merged my last pull request. Let's have a look. I should still have an outstanding pull request in here. Yeah, so actually that's my pull request right there at the top. So if you have a look at my change, this is for the simple linked list problem, and the test file name was wrong. So they haven't approved that one. Doesn't matter. I'll do another pull request based on the head of origin. So what I'll do is I'll go back to my master branch, check that out, and I'll branch off the master branch. And what we can call this is Hamming Fix Spec. We'll just call that there. Okay, so now we're on the Hamming Fix Spec branch. I'm going to jump back over into VS Code. I'm going to open a new window and open just the Exercism Elixir code base. Computer's a little bit sluggish because of streaming, I guess. I'll open, which one is it? It's the hamming.exs. And we can see here that we have our incorrect spec. So the spec here is saying that it should return a non-negative integer, but if we look at the tests and also the documentation at the top there, it should be returning OK and the non-negative integer, or error, if we go into the test, or error and a string. Okay, so we've already updated that in our one here. So this is our updated spec. I'm just going to paste that in there. So as you can see, we have the two return options, OK, non-negative integer, or error and a string. And what we'll do, now that we've updated that, I'm going to jump back into source tree. I prefer to use source tree. I like a graphical representation of my any sort of Git repos. It just helps me to make sure that I don't have mistakes. The one really cool thing about source tree is that it really allows you to very easily pick and choose between things that you've changed. So you can split them between commits and just be very, very clear about what the commit does. So typically a single commit shouldn't do anything that you need two sentences for. You shouldn't have to say this changes this and it also implements a totally new function. My general feeling is that you should implement new functions in separate commits. Anyway, here we're only making one change, right? So what we're doing is we're fixing the spec. So I'm going to stage that file, Shift-Command-C to prepare it. And what I'll say is fix the spec for Hamming problem. Do I need to explain it anymore? I think that's probably fine, to be honest. And what I'm going to do is I'll just commit that. I won't push it just yet. I just want to make sure, and this is a really good thing about source trees, I can just make sure that my commit is all looking fine, right? So we have our new commit there. And it's probably okay. And what we want to do, instead of committing again, is we want to push that to the origin. The origin is mine. So we get our Hamming fix spec. We'll push that to the origin. We'll see that come up in my GitHub. And we'll just make sure that everything's come through properly. Okay, Hamming fix spec is now pushed to the origin. Okay, and you've already seen that come up. I don't actually need to refresh. So GitHub has very helpfully put a little button there that says compare and pull request. So what I'll do is click that button and it will come up to here. I'll leave a little comment. Original spec does not match the documentation and tests. Okay, so we'll just double check that the branches. So we've got Percy Grunwald Exercism Elixir, which is my repo on the Hamming fix spec branch, and we want to merge it back into master for Exercism Elixir. We've got our title, and we've got the little description there. I'm going to create a pull request based on that. Happy days. So now we have another pull request. I have the 2 most recent pull requests on this repo, and we'll see if they merge it in. They're not major changes anyway, but I thought I may as well be helpful, and this might actually be helpful for anyone that's considering contributing to open source. That's really all you do. You fork, you update, you push to your local repo, and then you do a pull request. So I might make some more videos about how to do that specifically, but for now, I think that we're all good. So that was a fairly easy problem. I'll update an article on the website to explain the way that I approached it. If anyone has any questions, please hit me up in Twitch, YouTube, Twitter. You can check the site for any more of our socials that you'd like to link to, and we'll see you next time.